Okay, in this second video, I want to work through sort of an example of how you would use all this kind of, all the theory that I've given you in a sort of somewhat practical way. It's an experiment that one of my PhD students, Tai Toomey, ran several years ago at this point. So it's real in that sense, and of course you can read all about it. I think the reference is at the very end. If not, I can just put it on Moodle for you, not a problem. But it's a nice example of a 2x2 design that allows us to look at how you might use this in practice. So I want to talk first in terms of what I mean by a 2x2 design, in the sense that it's a factorial design. We talked about this a little bit before in advanced experimental designs when we were talking about regions of interest, right? So one of the debates was, is it better to have an independent functional localizer, or is it better to have a factorial design where the functional localizer component is orthogonal? It's one of the factors in your design. In practice, what that means is we have two factors, and they each have two levels, A or B, right? Which means that all told, we have 4 cells in our design, 4 conditions, right? So the first factor, which is shown on the x-axis here, I've said has 2 different possibilities, A or B. The other factor has 2 different levels, 1 and 2, and it means that you have 4 cells, A1, A2, B1, and B2. I assume that you've seen this before and that it's very straightforward. If you haven't, you're probably looking at it and thinking it's still very straightforward. So let's make this a little bit more concrete. So the experiment that Tai ran several years ago related to reading words in Japanese. Turns out, Japanese is kind of a cool language in the sense that they use 3 different alphabets in common form all the time. So in English, we just have the one alphabet, and when you write a word, there's only really one correct way to write a word. In Japanese, that's not true because they have 2 different, well, 3, but I'm going to simplify it here and use 2 different scripts. Right, so you could write the word in kanji, which are the logographs. That is to say, the characters that Japan borrowed from Mandarin many years ago, and of course over the years they've switched in terms of how they're used, so that Japanese kanji and Mandarin aren't the same anymore. But you can also write it in a syllabic kind of form using hiragana, and one is sort of a sound-based form, one is just a visual form. But they're both routinely used, right? So if you wanted to write apple, you could write it in kanji as one character, or you could write it in hiragana as a set of characters that spell out apple. But either way is fine, and it's equally correct, and it's used in common form. Japanese is pretty much the only written language in the world at this point that routinely uses 2 different scripts for the same potential words. There are other languages, like in Mandarin, you have the Mandarin characters, and of course, children are taught to read using a technique called pinyin, which is very much like hiragana, but it's only really used in teaching to read. By the time you're an adult, you're using the characters full time. So this is what makes Japanese unique. And what's interesting about this, and the reason I've taken so much time to explain this to you, is that that means that there are ways that people are used to seeing a word in Japanese that are different from the word itself. So that is to say, it turns out, I think I'm going to get this right, that when you write man-made objects like telephone or desk or chair or something, you're more likely to use kanji than you are hiragana. Either's fine, but it's just typical that you would use kanji. In contrast, natural things like fruit and vegetables or whatever, or trees, you typically would write in hiragana, although it's perfectly fine to write it in kanji too. So that is to say, there are words that you're used to seeing in one form, words that you're used to seeing in the other, despite the fact that both are the same word. And then there's some that are written either way and it doesn't matter. So what Tai did in this experiment, her first factor was the script that you write a word in. That is to say, it's either written in kanji or it's written in hiragana. Those are the 2 levels of the script factor. Then the other is the visual familiarity. How often do you normally see this word written in kanji versus written in hiragana? And the words that are written more commonly in kanji would be those that are highly visual familiar, and the ones that are less commonly written in kanji are the ones that are low visual familiarity. So you have a high-low levels of this factor, visual familiarity. Okay, so you have 2 factors here, script and visual familiarity. Script can be divided into kanji and hiragana, and visual familiarity can be divided into high and low. And the question that Ty was asking was, what is driving the response? Is it the nature of the word? So is it the fact that the word is apple, regardless of how it's actually written? Or is it something to do with what you're most used to seeing? Is it the case that you normally see apple this way and you see truck this way, and therefore those are the things that you've visually learned over time, and it really isn't anything to do with the nature of the word truck. It's actually the way it's written that you're familiar with. That was the question she was trying to get at. And Japanese really is the only way to do this in the modern world without making up a language and teaching it to a lot of people. Okay, so what she ended up using was what's called a lexical decision experiment. This is an experiment where there's a word written on the screen, and then you have to decide, it's a word or it's not a real word written on the screen. So if you saw, in English, if you saw the word apple, you would push a button and say, yes, apple is a real word in English. If you saw the word blork, you would push the button, no, blork is not a real word in English, even though it's composed of plausible letters and sounds and things. So she did this in Japanese with Japanese participants here in London, because there are plenty of participants around. And the words come from those 4 different conditions. So that is to say, there are words that are written in either kanji or the same word written in hiragana. And that word is either more commonly written in kanji or more commonly written in hiragana. So there's those 4 aspects of those cells. In addition, there are non-words on the screen. That is, things that the subject's saying no to. In order to keep people honest in doing the task, it's important that they're not sort of saying yes all the time and no just infrequently. So they're saying yes and no sort of equally, which means that there's a lot of these non-words in the experiment. The non-words aren't interesting in terms of the analysis. They're only there to keep people doing the task honestly, so we can keep them attending. Nonetheless, they form an important part of the experiment. In addition, people don't always get all these right. Occasionally you push a button and think, oh man, that wasn't right. What I really meant to say there was no, that's clearly a non-word, but I messed up. So as a result, we end up with this sort of much more complicated design matrix than you would with just a sort of finger tapping task, on, off, right? Really simple. Now we have a series of columns that correspond to these different conditions. First of all, we have kanji words that are typically shown as kanji words, so high visual familiarity. Kanji words that are typically shown as hiragana words, so low visual familiarity. Hiragana words that are typically shown as hiragana, high visual familiarity. And hiragana words that are typically shown as kanji, so low visual familiarity. So we have 4 conditions. Plus we have all the non-words, 5th condition. Plus we have errors, a 6th condition. As a result, we end up with 12 columns in our design matrix because we have those 6 conditions and their temporal derivatives. And that's what's shown here in this design matrix. The other thing to bear in mind is this is an example of an experiment that takes a while to collect enough data because there's so few items in each condition. So after about 12 minutes of a run, we normally would stop, give people a break, and then run a second run of another 12 minutes. So rather than just go full on for 24, 25 minutes, we would break it into halves. So there's 2 runs, which is why there are 2 parts to this design matrix. There's the upper left-hand corner, which is run 1, and then there's the lower right-hand corner, which is run 2. It's the same participant in both cases. So we have 2 first-level analysis, one from run 1, one from run 2, that we're going to combine with a fixed effects model into a subject 1 analysis. And what I'm showing you is the design matrix here for doing exactly that. So this is the example that I was talking about earlier. This is a very typical way of collecting the data. And then you can see on the far right columns, there are 2 constant terms, one for each run. And again, that just takes away the mean activity across the whole brain for run 1 and run 2. So the fact that you've stopped and started the scanner twice doesn't change. It allows you to deal with the fact that there could be changes to the absolute values of those numbers by simply just demeaning them. Okay, so as I say, what we're looking at here is technically a second level fixed effects analysis of one participant's data from 2 separate runs, which is a normal scenario. That's why I don't like to call the group analysis a second level, because technically this is second, and when we combine this participant with the rest of the participants in the experiment, we're at the 3rd level, because there's a group level analysis. Okay. And look, I should just add that I'm taking some time to explain this experiment, not because I need you to understand this experiment in any detail. It's irrelevant to your knowledge of fMR. I just think that when you get a grounding in like what was done and why, and what that means in terms of the analysis, the design and analysis, that's the kind of information that hopefully will be able to generalize to the type of data that you'll be looking at, for instance, in your projects. So I've taken some time to explain Ty's experiment, but really understanding the details of Japanese writing systems, irrelevant to me. I don't care whether you get that or not. Hopefully I've made it clear enough that you can follow along, but that's all I really care about. Okay, so when we do the group tests, then what we want to do is take the effects from the first level and bring them up to the group. Now, in this case, because we have something more complicated than finger tapping versus rest, we have multiple contrasts that we might want to get. And in a 2x2 design, classically, there are main effects and there are interaction terms. So that's what I want to focus on. So a main effect would be, independent of the levels, is there a difference between reading kanji and reading hiragana? That's a main effect. Similarly, the other main effect would be to say, independent of which script it was in, is there a difference between words that you see in their high familiarity form and words that you see in low familiarity form, right? Those are the two main effects in this particular 2x2. The interaction would be a combination of those things. We'll get to that in a second. So let's just consider this main effect of script, right? Is there a difference when you're reading kanji words relative to hiragana words? Well, then what we need to do is create a contrast vector from our first level that extracts out the conditions that are relevant for kanji and hiragana and ignores all the rest of them. So we have a much more complicated, it's not much more complicated, contrast vector, right? Which is shown here for a first level run. So what I'm interested in are the kanji cells in this design. And in this particular case, you can see I've highlighted them in blue. I care about the kanji condition and not its temporal derivative. In general, temporal derivatives are things that I'm just not going to pay any attention to, which means that almost always every other value in my contrast vector is going to be a 0, because the condition is something I might be interested in. The temporal derivative is not. So I take the two kanji forms and I want to subtract from those the hiragana, because what I'm interested in is where is kanji more than hiragana. So I'm going to say kanji minus hiragana. If they're the same, you're going to get 0. If kanji is greater than hiragana, then you're going to get an effect. That's what I'm interested in. Okay. So this is the contrast vector. You can see that there are 4 1s and 0s that are highlighted, corresponding to kanji and hiragana. And then there are 4 values there that are not highlighted, that are black at the end, and those correspond to the non-word condition, which I don't really care about. It's not interesting. It's only there to keep them honest in doing the task. And the things that they made a mistake on. Any item that they actually made an error on, I'm just going to exclude. I'm only going to pay attention to when they get things correct, because that's when I can at least say, I understand the cognitive processes that are going on. When they've made an error, it's hard to know what was happening. Were they not paying attention? Do they not understand? Do they not know it? Any of those things is possible. So rather than deal with those, I'm just going to exclude them post hoc, because like many of the experiments I've talked to you about, this was a combination of a blocked event-related design, and because there was an event-related component, I can post hoc separate out the things that were correct from those that were incorrect, and I just treat the incorrect all as something I'm not interested in. So that is to say, the non-words and the errors are shown there, and because I'm not interested, they just have 0s in the contrast vector. There's a set of 3 dots because I'm only showing this for the first run, but for one subject, that would actually be repeated twice, right? Because there's run 1 and run 2. The pattern's the exact same. So rather than try to fit all that in one screen, I just showed it this thing one time. So let's just say you get a main effect, right? So the activation that's shown here that includes Broca's area and parts of the occipital temporal zone is what you find out. So when people are reading kanji, there's significantly greater activation in these blue bits that are shown on the brain than when they're reading hiragana. Well, what's going on? So the interpretation that I've just given you is that what's happening is, yeah, kanji is giving you more activation than hiragana in those places. And the bar plot shown on the left is intended to sort of illustrate that, with kanji shown in those dark gray bars and hiragana shown in the right. I mean, it's a main effect, so that's what we're expecting, right? Independent of whether it's high familiarity or low familiarity, kanji, dark bars, should be greater than hiragana, which is the light bars. That's what you sort of intuitively anticipate is going to come out of a main effect. However, you can get it lots of different ways, right? Because if you consider that contrast vector, one way that you could still get a positive value would be a pattern like this. It could be the case that it was a main effect, but it's really, really driven by one of the languages and not the other. So you can see in this particular version of the plot that, for high familiarity words, there's just no difference between kanji and hiragana. Those two bars are essentially the same. It's these low familiarity words here shown on the right where there's a huge difference. Kanji gives you a massive activation, hiragana gives you virtually nothing, and as a result, the difference there, averaged out, is going to still show a greater advantage for kanji than hiragana, but it's entirely driven by this interaction term, by the fact that it's only there for the low familiarity words. Okay, but even though I typed in a contrast that corresponds to that main effect, this is a pattern that I could get out of it. It's a perfectly plausible interpretation of the data. And if I didn't look at the bar plot showing the effect sizes, there's no way I would know. But wait, it gets more. So this is also a way of getting a main effect, right? And this is starting to get counterintuitive because let's just say 0 in this case is rest. When people are not doing the task at all, they're just sort of resting in between blocks. In this scenario, kanji, which is the dark gray again, is still higher than hiragana, but it's only higher than baseline in the high familiarity case, right, which is shown on the left. In the low familiarity case, it's below baseline. That is to say, rest is more active than either low familiarity hiragana or low familiarity kanji. So what's going on there? Well, look, there's still a difference here. Even though it's negative, the low familiarity kanji, which is the rightmost dark gray bar, is less negative than low familiarity hiragana. That is to say, there's a difference between them, and that difference is in the same direction. It's not at all what I was looking for in my main effect, but it is numerically still capable of generating a main effect. So if this is the pattern that I see, it's a really different interpretation of the main effect than what I had initially thought. And still worse, they could all be negative. You could actually see a pattern like this, where all of the activation was less for reading than it was during rest. But it was more deactive for hiragana than it was for kanji. And that is absolutely not what I'm thinking about in most cases when it comes to a main effect. And yet, numerically, this is exactly something that you can get out of that correct main effect vector. So the problem that we face here is that mathematically, all of these are main effects. Intuitively, only one of them is what we really are interested in, what we're thinking about. So how do we exclude the things that aren't what we want and focus in on the things that are what we want? And that's where inclusive masking comes in. And this is why inclusive masking is not only powerful, it's absolutely essential when you're trying to do almost anything with fMRI. If all you've got is a finger tapping task and you're only comparing finger tapping to rest, I can imagine a scenario where you don't need to use inclusive masking. If you have anything more complicated than that, you will need to use inclusive masking when you're analyzing your data, when you're writing it up. Just fair warning, it's a super important part of understanding what's in your data. And for the reasons that I just said, I'm going to explain in further detail, but that's the whole purpose of this video, is to make this all kind of concrete with a particular example, right? So if I'm interested in this main effect of kanji versus hiragana, then my assumption is that, first of all, the activation is going to be present for kanji more than rest. So that is to say, I want positive activation values. I don't want values that are below 0. I'm not interested in relative deactivations. That's just weird. There are people who are interested in relative deactivations. We may end up talking about it at various points. But for our purposes, it's probably not the first thing that comes to mind. So I'm probably also interested in scenarios where hiragana is more than rest as well. That is to say, I don't want kanji to be bumbling around just slightly above rest, but maybe not significantly active relative to rest, but hiragana to be below 0, and therefore the difference is a positive difference. That doesn't make sense either. So there are 4 conditions here that I want to have met. I want to make sure that high familiarity kanji is more than rest. and low familiarity kanji is more than rest. So both kanjis are more than rest. Similarly, I want to say that high familiarity hiragana is more than rest, and low familiarity hiragana is more than rest. Both conditions of hiragana are more than rest. Okay, and that'll help by eliminating possibilities and ensuring that we're only looking at positive effect sizes, right? Because that's what we're interested in. But in addition, so that is to say, like if of the 4 possibilities that I just showed you in the last couple of slides, if those 4 conditions are met, then those last 2 possibilities shown there on the right can't be true anymore, right? Because in the third one, the first one with an X in it, 2 of the values are below rest. So in other words, hiragana, low familiarity hiragana, and low familiarity kanji are both below rest. So therefore, they don't meet conditions 2 and 4. Does that make sense, I hope? Similarly, all 4 conditions in the right are below rest, so it doesn't meet conditions 1, 2, 3, and 4. The way we do this is using something called inclusive masking. That is to say, we specify a contrast. Let's just take the first one, kanji high versus rest, which is a separate contrast in our model that allows us to sort of say, well, here are the parts of the brain that are active in kanji high versus rest at whatever threshold you picked. If you just turn that into a binary mask and say, I don't care how active or they are, all I want is any voxel that's active is going to be a 1, and anything that's not active is going to be a 0. Well, then you have these little regions of activation that you could treat as a mask. And you could say, okay, well, I'm only going to look in those areas inside these masks because those are the conditions that meet this contrast. High familiarity kanji is more than rest. That's true for a single mask. If you have multiple masks, you do the same thing with each of them and then overlay them so that you're only looking at where things meet all of those masks. So in this case, I want them to meet 4 different conditions. I want to only look at parts of the brain that show more activity for kanji, high familiarity kanji than rest, low familiarity kanji than rest, high familiarity hiragana than rest, and low familiarity hiragana than rest. So it's the more conditions you have, the more inclusive masks that you add, the more restricted you are, but nonetheless that allows you to eliminate possibilities that aren't of interest. In this case, with those 4 contrasts, we've eliminated 2 of those possibilities. If we add 2 more contrasts and say, I also want to know where high familiarity kanji is more than high familiarity hiragana, so kanji more than hiragana for high, and kanji more than hiragana for low, then I've eliminated the other 2 possibilities and I'm only left with 1, which is the main effect that I think we were most interested in. Namely, you see that there's an advantage. The gray bars are higher than the white bars, but each gray bar is higher than each of the corresponding white bars, right? That's a true main effect of the sort that we're thinking of. Now, the only way we got that was by putting in the correct main effect contrast vector. I didn't make any errors. I didn't make any omissions. I did it exactly correct. But then I included 6 inclusive masks to say it not only needs to be this main effect, it needs to meet these 6 additional conditions that are specified here on the screen. In doing that, I end up with the main effect that I'm most interested in. Okay, so how does that end up happening? Well, typically what happens is after you've done your first level model on SPM, but it may be first and second if you had multiple runs and you're combining them per participant, but you've done your fixed level analysis, then you're going to combine them by bringing the key parameter estimates up to a group level model. In SPM, we're going to call it a second level model, but it may be second or third level. It doesn't really matter. And the important thing is, in our experiment, there were 4 conditions of interest. They were the 2 high and low familiarity kanji and the 2 high and low familiarity hiragana conditions, right? And they corresponded to particular beta values in each person. So we can use linear contrasts to bring those up to this group level analysis and put them together into what amounts to a simple ANOVA. And this would be the design matrix of this. So for this week, there's a lab that will do exactly this. Actually, that's not true. I'm not entirely sure it's this week's lab. Maybe it's next week's lab. But nonetheless, the key is that you'll have the opportunity to do this experiment with these data and go through the steps that we've talked about in these videos with the actual data in order to get familiar with the process. So we'll go through the step-by-step sort of cookbook recipe of how to do this in lab. But what you end up with is this relatively simple design matrix where you have the beta values, so let's just say that high familiarity kanji was our first condition, then that means beta 1 corresponds to words that are written in kanji and that are highly familiar to people. And let's just say you have, I only put 4 subjects because that's all I could fit in on the screen, but I think that there are, I don't know, 16 or something in the actual data set. But they all then get put in this first block. Then similarly, beta 3 is low familiarity kanji, and they'll get in the second block. Beta 5 is high familiarity hiragana, and beta 7 is low familiarity hiragana, excuse me. So the reason that those are the odd numbers is because in between are the temporal derivatives, right? So beta 2 would be, for instance, the high familiarity kanji's temporal derivative. And I don't really care about temporal derivatives, so it had a 0 value in the contrast. I'm not going to bring it up to a group level analysis. And with that, you can compute 7 different contrasts, right? So you can compute a main effect. Sorry, what I meant to say is if you're going to compute a main effect, you're going to need 7 different contrasts. You can compute a main effect of high versus low familiarity or whatever the case, whichever main effect you're interested in. And then you're going to need those 6 simple contrasts to use as inclusive masks in order to ensure that the main effect is the main effect that you're really interested in and not one of the other numerically valid options that isn't intuitively what we're thinking about when we think about main effects. When you specify a main effect, when you specify inclusive masks, you have to say at what threshold you're going to mask the data at. So you could do it at a corrected level. You could say, well, I'm going to make sure that each of my masks is only including voxels that are there after you deal with the multiple comparison problem, which we'll talk about next week. Or you can use a sort of more lenient approach and just say, look, I want it to be numerically in the right direction, but I don't really care that much if my masks are significant at a group level. All I want to do is ensure that it meets this sort of criteria. And by default, SPM uses an inclusive masking level of an uncorrected P of less than 0.001, which is a perfectly fine thing to do. You could be more lenient. You could make it a p-value of like 0.01 or 0.05 if you wanted. Whatever masking you do is fine as long as you specify in your write-up what it was, right? So there isn't any theoretical reason to choose one threshold for a mask over another. They're all fine. But it is kind of essential to explain to the reader what you did choose so that they know what level of restriction and exclusivity you're using on your data. Okay, so when we think about this particular kind of 2x2 design, there are 2 things to bear in mind. One is that when we're looking at these main effects are by definition 2-tailed, but I've only showed you 1 tail. So when I said I'm interested in what's more for kanji versus hiragana, I thresholded it out so that I only showed you the things that literally were more active for hiragana for kanji than hiragana. But you could look at the other side of that and say, well, actually, what's more interesting is what's going on with hiragana relative to kanji. If you're only looking at 1 tail of your data, which we always are with fMRI data and the kind of software packages, then you just have to invert the contrast, right? So if kanji more than hiragana is -1, 1, -1, 1, then if you want to do the opposite, multiply the whole thing by -1. You get 1, -1, 1, -1. They're shown here on the screen. This is true for interactions too. Interactions by definition are always 2-tailed, which means that if you're going to look for an interaction, you need to make sure you look for both tails. It's not sufficient to only ever look at one, unless you have some really strong a priori hypothesis about why your interaction should only be 1-tailed, in which case maybe you can get away with only looking at one side of it. But you should just bear in mind that interactions by definition are always 2-tailed. So it's important that you look at both sides. And that means entering a separate contrast to look at the positive side of the interaction and a separate contrast to look at the negative side of the interaction, which are both shown here. Okay, I know there was a lot of information, and I know it was challenging to take that in the context of an experiment that you didn't design, and maybe you've never ever thought about writing systems and how that affects brain activation. I get that. That's a challenge, and I appreciate you sticking with me through this. It's possible that you may want to look at this video again and just take it slowly so that you know where I'm coming from. But the take-home messages from today are that we're going to use linear contrasts to interrogate our SPMs. And by definition, we will always use one-tailed versions of these. So if you're interested in why A is greater than B, that's great. That's a one-tailed question. But if you also want to know where is B greater than A, then you need a second linear contrast to do that, because we're only going to use one tail. Second, and a really key point that I hope everybody gets, but it'll be really emphasized more in the labs and then in particular in your project as you actually look at the data sets that you have, is that a contrast can be significant for a lot of reasons. All it is that linear contrast where you're multiplying those contrast vectors by your beta values and trying to get a number, right? That's your effect size. If the effect size is positive, you can get it because of lots of different ways. And I illustrated that with this the particular experiment today. But it does mean that when you're interrogating your data, you almost inevitably need to use inclusive masking to look at your data. I would also recommend using effect size plots so that it's relatively easy to visualize these things. But we'll talk about that a little bit more in 2 weeks' time, actually, at this point. When you're doing second level or group level analyses, there are multiple different ways to do it. I've actually only gone through one of them today using a sort of higher level ANOVA because that has become the default for the community. There are other ways of doing it, and if you're interested in that, we can talk about them. They're more relevant sort of historically. People don't really use them anymore for a variety of reasons, but theoretically, the approach that I've given you today is the optimum approach, and practically it's also the much more simple one to actually implement. When you're thinking about what's the right group level analysis to do, second level analysis to do, then you can be thinking about whether you want to do a fixed effects or a random effects analysis. The fixed effects analysis is perfect if you're not interested in expanding your inferences to the population. All you care about is what's happening in the data set in front of me. Fine, then you don't have to pay any attention to between subject variance. On the other hand, if what you really care about is if my sample of data is representative, then I'd like to be able to extend this generalization to the population that they're drawn from, then by definition you need a random effect or a mixed effects analysis because you need to take into account between subject variance. Often, in practice, you'll use both because if participants are experiencing more than a single run when they're doing the data collection, then you're going to use a fixed effects analysis to compute a subject level estimate, right? What did this subject do across the multiple runs that I have of this person? And then you'll use that subject level analysis in a random effects analysis where you can start to estimate between subject variance to estimate how this data would generalize to a larger population. So both of them are going to be relevant to you under almost all normal circumstances. If you only collect one run from participants, then you can skip that fixed effects level and jump right to the random effects analysis, and that's perfectly valid. As always, bit of a reading list. Yeah, and the Tai Toomey paper is there. I thought it was. But some of these papers are seriously dense. So Ty's paper isn't, it's more about the cognitive neuroscience. But for instance, there's this Christian Beckman paper about general multi-level linear modeling and the Carl Friston paper about mixed effects in fMRI. Those two papers are really challenging, but absolutely worth your time trying to work through in as much detail as you can. And it'll depend on your particular mathematical backgrounds, right? But for anybody who's not a total math geek, they're going to be challenging papers. I get that. I would still recommend that you make an effort because this becomes a really important thing in understanding what is happening at the level of these models and how do we get this information and what are the implications for it. So it's not easy reading, but it's very, very valuable reading. Similarly, the Keith Worsley and the Mark Woolwich papers and the Will Penny papers, like the first two. They're like the Beckman and Friston papers. So I wouldn't necessarily recommend sitting down and trying to power through the lot of them at once. That would be a massive challenge. It took me a long time to read these and work through them over the course of my career. But I would highly encourage you to take that time and effort. And certainly the place to start really is with chapter 6 in the Poldrack book, because that's going to give you the overview and a lot of the interesting details. Then these papers will allow you to drill in much greater detail. If you're planning to use fMRI in your research, in your career, these are kind of essential papers. Really, really critical. I will stop belaboring this point and wish you the best of luck with them. As I said, when we get to do the lab and do this stuff in hands-on, it becomes a little bit more concrete, and you get to see how these things play out in terms of the way the software happens and the results that you get out of them, which is a very, very satisfying process and is exactly what you're going to need to do when you're doing your project and looking at your own data. Thank you very much.